Okay. Good morning, everyone. My name is Khaled. I'm from the Intelligent Multi-Robot Coordination Lab in Technical University of Berlin, under the supervision of Professor Hünich. And today I'm going to present my work in motion planning for cable suspended payload transportation with a team of multi-rotors in cluttered environments. So first, I'll provide you with an introduction and a motivation to our research. In the last decades, UAVs have been considered ideal for tasks that are involving accessing remote and dangerous places, which makes them also reliable to collaborate collectively in a variety of scenarios. And one of these scenarios could be even in construction tasks, which is already existing in the literature. And in order to advance in this research, researchers have been working on studying the modeling of such complex systems and also developing motion planning and control algorithms. One of the tasks we are interested in, which is we see a lot in the construction sites and scenarios, is to actually just remove this. Is to actually, as seen on the figure on the right, you have two UAVs connected to a bridge-like payload with cables, and it's required to place this bridge on top of the two construction columns while going through some obstacles. And in order to achieve such task, initially the UAVs should take off, pass through the narrow passage while changing the formation of the team, and finally place the bridge on top of the two columns. So there are multiple methods in the state of the art that try to solve this problem. And to sum up the challenges and the drawbacks that are there, which gives me the motivation to work on different directions. One of them is they either don't include inter-robot collisions, like collisions between the robots themselves, or the robot obstacle collisions. And this is one crash using one of the state-of-the-art methods, carrying a very small payload, which is also another direction if you have different sizes of a payload or even different sizes of UAVs. And of course, some of the methods have already provided some solutions, but most of them are even very expensive in terms of computations. In order to introduce our contribution in this work, I'll give you a little background about my previous work. So, as you see in this figure, this is the full framework that we use to plan and control for the cable suspended payload system with multiple UAVs. The first block is generating the reference trajectory, and the rest is the control loops, 3 control loops, starting from defining controlling the payload pose up until the low level of the UAVs. And our previous work was actually in the control side, where specifically we extended one of the existing state-of-the-art controllers, which takes into account the inter-robot collisions between the UAVs themselves. And we did that by defining a cable force allocation optimization formulation. And when we try to solve that, we basically solve for, given the collective force we want to apply on the payload, we try to find what kind of force vectors that we can have at each cable, which gives us also the formations of the UAVs. And to sum up this complex design of work, it's a cascade of carefully designed quadratic programs that can be solved efficiently and also in real time. Getting back to our work and explaining the approach, we contributed to the pre-processing part, the reference trajectory generation part. And we basically defined an offline motion planning algorithm where we plan not only for the payload states, but also for the cable states. And we have the opportunity to plan for the cable states because we can leverage our previous optimization formulation that we had in the cost function. So in order to move on with how do we actually define the offline motion plan, we basically depended on sampling-based motion planner, and I would like to give a bit of a background. So basically given an environment with obstacles and the start and the goal configuration, you first sample a random configuration, and you try to find the nearest neighbor of this configuration, and you connect it towards the direction of this random sample with some predefined metric as x nu, as defined in the below plot figure. And then you keep doing that until you have a tree-like a roadmap, and then finally you search for the path from start to the goal. So getting back to our contribution. So the key idea, as I said, is to plan for the cables and the payload states using sampling-based motion planners. And we plan for them geometrically using this planner. And what we use is we optimize the sampling-based motion planner by defining a cost function that minimizes the energy of the system. And by this means that we try to find the formations the formation that makes the system stable with respect to the quasi-static formations. And eventually, when we have the geometric states of the cables and the payload, we can define the first order derivatives, and thus we can have the full reference trajectory that we can provide to the controller, which will be tracked by it then. Moving on to the simulations and results. In order to provide an evaluation and validation for our method in terms of performance and solution quality, we define 3 different environments. We have the empty environments with 8 UAVs, and we have the forest-like environment, and also we have a narrow passage environment, which imitates what we have seen in the first image, basically. And to show our results, this table encodes our results, which you can also find in our paper. So basically, this table describes the relation between across different environments. You have different metrics that you want to see, and with respect to the number of robots. We start from 3 robots up to 8 robots. And the metrics we used, we check the cost over 10 runs, the average cost of the first solution for the 10 runs, the time for generating the first solution, and the success rate over the 10 runs. And basically what we have found in this table, as shown in this red box, for the first solutions, we have high success rate and relatively low costs in the empty environment. However, with obstacles, as we notice, success rate decreases as the number of robots increases. And as you can see, the motion planner couldn't find solutions for the 7 and 8 robots. And this brings us to the next step, which is the challenges that should be some part of the future work. So as we know, sampling-based motion planners always suffer from the curse of dimensionality, which is usually a problem. We try to reduce the state space as much as possible, but still we need to work a bit on that. And second thing is the way we reject the samples that are either in collision with respect to the cables colliding with each other, the UAVs colliding with each other, or anything colliding with the payload or with the obstacles. And finally, the interesting part is to show you an experiment which we did in our flight space in the lab. So these are the 2 UAVs carrying the bridge with cables, and then they take off. They start following the desired trajectory. They orient themselves, they change the formation of the team until they reach over the 2 construction columns. They rotate, and then they try to adjust the position of the bridge as desired. And then they land. So to wrap up and conclude, we introduced a geometric sampling-based motion planning algorithm, or used one of them that is feasible and efficient on such a complex problem. We verified our results and opened some research questions to the next steps using simulations and physical experiments. This is also shows that there is a potential for more complex construction tasks. And as discussed, for the future work, we are also interested to see why, for example, it didn't work for 7 and 8 robots when we are in a very dense environment. So we look more into the scalability and also to see how can we enhance the solution quality by using some of the techniques that usually the literature says in the motion planning direction, which, for example, shortcuttings of the generated path. And this work shows that it can be like one of the plans that we have is to extend the current work to multiple teams operating in the same environment, carrying payloads and doing different tasks. Thank you. And please, if you have any questions, and this is the QR code for the paper if you want to check it out.